Okay, so our last speaker of the morning is HChe, who has been in the festival many times, and she's going to tell us about electromagnetic electron Kelvin-Helmholtz instabilities.
Okay. First, I want to give a small advertisement to our department. I think the space science department perhaps is the only one department uniquely in space science in USA. we include from the magnetosphere to solar wind to solar physics and also astrophysical physics. Integrate the plasma into the space science. Okay, today I'm going to talk about the electromagnetic electron current instability. First, I want to acknowledge the NSF Career and the NASA Heliophysics Career Award. Do we have one? Okay. I think we are all familiar with the Kelvin-Helmholtz instability. If you would like to look up the sky, it's very common. You can find such kind of clouds with vortices. That's a kind of the vortex. So this is caused by the shear caused by the warm wind above and the cold wind speed below, and cause Kelvin-Helmholtz instability in the sky. Kelvin-Helmholtz instability is very common in fluid, and it's also very common in plasma. This is a discovery of the Kelvin-Helmholtz instability in solar corona. You see, this is cause similar patterns to the clouds. Here is an animation of the Kelvin-Helmholtz instability. The Kelvin-Helmholtz instability, one of the characters of Kelvin-Helmholtz instability is the vortex formation. This is perhaps why the Kelvin-Helmholtz instability has been attracted a lot of attention in the study of the turbulence. Before we move to the electron Kelvin-Helmholtz instability, I want to first talk about what is the difference between the neutral fluid Kelvin-Helmholtz instability and the MHD Kelvin-Helmholtz instability. Because Kelvin-Helmholtz instability in plasma was first studied in the MHD scale. In neutral fluid, obviously, Kelvin-Helmholtz instability without the generation of the electromagnetic field. In plasma, the most similar Kelvin-Helmholtz instability to neutral fluid is MHD scale. Kelvin-Helmholtz instability also maintains the plasma neutrality. So MHD Kelvin-Helmholtz instability is very similar to the fluid. However, MHD Kelvin-Helmholtz instability is coupled with Maxwell equation, generate both the fluid and the magnetic vortices together with electromagnetic waves. So this is a big difference between the fluid HChe and MHD HChe. MHD HChe generates the electromagnetic waves. So MHD HChe has been studied for I don't know how many years, more than half century. We have already understand almost very well about this instability. So if we think deeper, what would happen if we have a velocity shear on kinetic scale, especially on the electron dynamic scale, what would happen? Do we have a similar HChe on kinetic scale? Recently, a lot of space observations discovered it's very common in magnetic reconnection to develop electron dynamic scale current shades with strong electron velocity shear and trigger electron scale HChe in a manner similar to the ideal MHD HChe, but with a much higher frequency and short wavelength. The HChe is usually associated with electron acceleration. This is a demonstration of the electron velocity shear in magnetic reconnection from my simulation, particle in-cell simulation. This is the VEX. X is horizontal. So you could see during the development of the magnetic, with the process of the magnetic reconnection, the VEX shear, the top, this is a bar that's minus and positive of here. This is minus, you see the black, and below, that's a shear developed during the current shear and develop the electron scale. So in the space, because we didn't have a theory about the electron scale HChe, so in the space observations, most people found the electron HChe is similar in a manner similar to the MHD HChe. So the people were curious to ask the first question is whether the ideal MHD HChe dispersion for step function velocity shear. This is the first analytic dispersion relation derived by Chandra Seta in 1961, can be extended to electron scale HChe. If we can do this, so it means we change the shear is the same, that's velocity shear, and then change it to the electron wave speed to the electron electron speed. So it seems much easier, and everyone is happy. So can we do this? This is a question we want to ask. So this is an easy question or not easy question. It depends on how we think. The first thing we have to understand what is the uniqueness of electron velocity shear driven current stability. Again, we have to say what are the difference between the MHD and electron dynamics. When we say the MHD or electron, this is artificial. This is because we define the MHD and electron scale. In nature, it's all. So for the level 1, the MHD scale is the largest spatial scale where the plasma is neutral. This is a very important characteristic of MHD. What does it mean? It means if this assumption has to be held, it means that MHD doesn't couple with the Poisson equation because there is no charge separation on MHD scale. And then the level 2, that we call that we have to apply the two fluid dynamics. On this scale, we have to distinguish the ions and electrons, even though they can be treated as fluid. On MHD scale, in collisionized plasma, ideal MHD floating collision is held. This way is the mean velocity of ion and electrons. Usually is close to the ion velocity. On the level 2, this scale is comparable to the ion zero radius, and the flooding condition of ions has to be broken. It means ions is no longer move with a magnetic field. It's not tied with a magnetic field, but still electrons are still frozen together with the ions, with the plasma. Usually, this is the ion diffusion region of magnetic connection. And the level 3, on this scale, we have treat ions and electrons as single particles. Usually, we have to use a single particle theory or Laplace equation in collisionized plasma. And this scale is about the electron zero radius. And both the flooding condition has to be broken. This is comparable to the electron diffusion region of magnetic connection. This is you could compare to the space scales. The MHD, you can treat the plasma as MHD in space. It's usually that how large this is 1 million? 1 billion. 1 billion kilometers. And you see for the ion, it's about 1,000, 10,000, 1,000 to 10,000 kilometers. For the electron, it's already to 0.001 kilometers to 1 kilometers. There's a lot of mesoscale gray area here. It's very difficult to see. This is ion flow, so you have to check it in every case. So now, let's see what's the difference between the MHD HChe and electron HChe before we do any derivation and the theoretical study. MHD HChe does not have ES mode and only have EM mode. This is because MHD plasma is neutral and is unable to produce charge separation. In other words, MHD equations don't couple with Poisson equation. And for the electron HChe, obviously, we can have both EM and ES mode. Today, I will focus on the electromagnetic chiral possibility. So, mathematically, if we compare the electron dynamics to the MHD, we can see electron dynamics is dominated by the electron fluid equation. The difference from MHD equation is that the electron momentum equation is also the generalized Ohm's law. If you recall MHD equation, you usually have two independent equations. One is the momentum equation, another is called the Ohm's law. And in the collisionized plasma, that we have the ideal MHD flooding condition. In the derivation of the temporal theta dispersion relation, ideal flooding condition is very important, play an essential role in the derivation because this couple with the Faraday equation for the derivation. So, and now, if we see the electron dynamics, we can see if the flowing condition still hold, what would happen? This term goes to 0. So the flowing condition splits the momentum equation as two independent equation. One is a pure fluid equation that is decoupled from the electromagnetic field. It means if you have a velocity share, this equation can give you a pure fluid velocity HChe. It doesn't have the electromagnetic waves. Can that happen on electron scale, electron dynamic scale? The answer is no. Obvious, no. And I tell you why. But first, that we can prove electromagnetic electron Helmholtz ability require the breaking of the ideal Fluorine condition. This is easier to show it because if the Fluorine condition is valid, and then the electron momentum equation can be reduced to this one. Yes. And from the Maxwell equation, it's easier to give this. And we can know the EM HChe wavelength is about the electron inertial length. And then the equation 13 gives this relation. However, from the electron momentum equation, we can see that one of the requirements for the ideal electron Fluorine condition to be satisfied, this condition is satisfied, it requires the inertial curves much smaller than the electric curve. Otherwise, this Fluorine condition cannot be valid. You agree? Okay. You see the contradiction now. So this leads to this direct from the momentum equation. So the contradiction of 14 and 16 means ideal Fluorine condition has to be broken when EM HChe is triggered. Of course, before that, the Fluorine condition can be valid. But once the instability is triggered, this condition is broken. Physically, we can understand this mathematical result as a pure electron fluid drives a fluid HChe, which generates a very low frequency electron and magnetic fluctuations. These fluctuations. And these low frequency fluctuations are unable to couple with a high frequency electron waves. So that's it. So if the Fluorine condition is not good, so what is the proper replacement for the ideal Fluorine condition in HChe? Because we are trying to see if we have a similar dispersion to Chandra cycle. So Fluorine condition is very important in the derivation. So if we don't have the Fluorine condition, it means we have to couple the whole momentum equation with the Faraday equation. In this case, we need another equation to close the equations. That is, we have to assume the pressure has a relation with some adiabatic expansion, something like that, to finish it. So if we want to, in that case, we don't have the Chandra HChe dispersion relation. So if we want it, we still want an easy, simple coupling with the Faraday equation. So how to do it? The answer is very easy. That is, we can replace the frozen condition by the magnetic flux conservation. Frozen condition is a special case of the magnetic flux conservation. Mathematically, if we understand the difference between the frozen condition and the magnetic flux conservation, we can think that frozen condition have a Lie-driven symmetry along the field line. But in magnetic flux conservation, it is not guaranteed. So physically, the picture is, if we have a flux tube, frozen condition guarantee the continuous changing of the shape of the magnetic flux tube. If the frozen condition is broken, it means at a location, something happens, dissipation of the magnetic energy. From the small sense, it can be called particle acceleration or plasma heating. It can be turbulence or loss turbulence, whatever. From the big sense, it can something big, explosive sense. For example, magnetic reconnection. So this is the difference between the frozen condition and magnetic flux conservation. If we have the magnetic flux conservation assumption, you see, again, we have the same Faraday equation. Now, if everything becomes so easier, and we can couple the continuity, the electron continuity and the momentum equation with the Faraday equation, with the standard algebras you can find from the Chandra Sekar book. We can obtain this equation, and at z not equal 0, because this is a step function profile. The equation is reduced to this Laplace equation. And if the boundary condition that at infinity, directly is 0, and we have solutions at the z larger than 0 and smaller than 0. And then we can integrate this equation over the interface z equals 0. We have this permutation. This is exactly similar to the HChe tetra, this permutation. The omega is equal to omega minus t dot u0. U0 is initial velocity above and below. And so if we solve these equations, we have similar discrimination to HChe tetra. The only difference is the arithmetic change the electron arithmetic. That's it. All other things are similar. And finally, I want to mention the threshold is correlated with the growth rate, because in the space pattern, sometimes the people always argue, because usually that one simple, we say, okay, the HChe growth rate is about electron plasma frequency, and HChe is much slower. And then you, oh no, the growth rate is not that high. in fact, when we really accurate, we can say the growth rate is related with the share. So the higher the share, the higher the growth rate. If we don't have a magnetic field and have the uniform density, you can say if the only requirement for the threshold is delta U greater than 0, the growth rate is related to the delta U. However, if we have a magnetic field, and usually the growth rate is not like this. The growth rate is about omega electron 0, and then you will find you need a much higher share threshold for the threshold. And the electron field HChe is relatively new and very interesting. They have very different, not very completely different. There are some difference from the HChe. For example, there's others, if we consider the electrostatic HChe, we found for in the open space, not in the confined space, for example, in the fusion, that if you have the boundaries and the electrostatic HChe occur without in the incompressible plasma. However, for the open space, the ES electrostatic compound stability can only occur in the compressible plasma. And it requires the velocity share is larger than the electron occulting. And if we have a transverse magnetic field, it will produce a new electron reticular instability. This is how the Fourier condition, before the occurrence of the HChe, the Fourier condition still holds. It has electric field. The electric field plays a similar role to the gravity. So it will create a new electron reticular instability. Another thing I want to say, when I started the HChe, I didn't consider the gravity. Why I didn't consider the gravity? The reason is because the field is so small. The gravity difference is small too, compared to the electric field and the magnetic force. Okay. Thank you.